Here's a bit of review on scalars. What's the average speed of an object that takes 2 seconds to travel 4 meters? Well, we know that average speed is equal to total distance divided by total time. And so 4 meters divided by 2 seconds gives us 2 meters per second. If the time interval required to travel the same distance decreases, the speed must have, well, since we're dividing by time, then the speed must have increased because the time has decreased to travel the same distance. So we're dividing by a smaller number. An object's instantaneous speed at any instant is always blank the object's average speed over the entire interval. Neither A nor B in this case. The object's instantaneous speed could be greater than the average speed, or it could be lower than the average speed. The idea there is that if the object's speed is not constant, then instantaneous speed is always changing. Or can change over time, in other words. Not necessarily always changing, but could be changing. So let's talk about experimental uncertainty. These are ideas that apply when we're doing experiments, not surprisingly. And it has to do with some tools that we use when we make measurements. All experiments have what we call experimental error. Those are not mistakes. They are limitations on the precision of the measurements that we make. And so sometimes we call them uncertainties because we are never 100% certain about the measurements that we make. We have what are called instrumental uncertainties, which are determined by the measuring device that we use. And we have procedural uncertainties determined by how the device is used. So, for example, a meter stick is usually, the smallest units on a meter stick are usually millimeters. So that means that there's a limit on the precision of that device. That would be considered the instrumental uncertainty. If we have a device that gives a digital readout, the uncertainty is usually provided by the manufacturer. Or, if not, we can assume the uncertainty to be plus or minus 0.5 of the last digit that we can read on the device. In this case, it would be plus or minus 0.05 grams, based on what we can see on the display for this digital balance. If we're using a certain instrument with divisions, like a ruler for example, then the uncertainty can be taken as plus or minus 0.5 of a division if the divisions are very close together, or plus or minus 0.1 of a division if there's more space to allow for an accurate measurement, or estimate rather, of the uncertainty. So let's determine the length of the screw in this diagram, including an estimate of the experimental uncertainty. Here we can see the divisions are 0.1 centimeters, and they're close together. So the uncertainty will be plus or minus 0.05 centimeters. It would be different if we didn't have the millimeter markings. So 5.1 plus or minus 2 times 0.05 centimeters, because we're measuring the location at each end of the screw, equals 5.10 plus or minus 0.1 centimeters. So the uncertainty at each end is 0.05 centimeters, and so that's why we multiply by 2. And the more measurements we make, the greater the uncertainty becomes. So we say that the uncertainty is cumulative. It just keeps adding up. So If in our experiment we were able to make fewer measurements, then it would be better because we'll have a smaller uncertainty. Procedural uncertainty must be estimated by the experimenter based on the way that you're using the tools of measurement. For example, reaction time. If you're using a stopwatch, well, a stopwatch can probably indicate hundredths of a second, but the human reflexes are only good to about 0.2 to 0.3 seconds. Repositioning error, such as when we're using a meter stick, if we're measuring the length of a football field, by lifting it and placing it back down repeatedly, the experimenter might estimate an additional uncertainty of 0.5 centimeters per lift, because it's difficult to reposition the meter stick perfectly every time. We wouldn't be able to do that. Here's one of those cases where it would be better if we could use, say, a measuring tape to measure the length of the football field, because we're only making one measurement. It would drastically reduce our procedural uncertainty, because the uncertainty always adds up the more measurements we make. So why do the uncertainties always add like that? Let's look at the addition of some measurements. Here we're adding 1.0 plus or minus 0.1 centimeters to 3.2 plus or minus 0.1 centimeters. So this shows us that the minimum value in the first case could be 0.9 centimeters, and the minimum value in the second case would be 3.1 centimeters. So that means that the minimum total, when we add those two minima together, would be 4.0 centimeters. If we do the same thing with the maxima, then we find that when we add them together, we get a total for our measurement of, or for our addition rather, 4.4 centimeters. So this shows us that our uncertainty is now, or rather our addition result is 4.2 plus or minus 0.2 centimeters, because it could be as low as 4.0 centimeters or as high as 4.4 centimeters. So our uncertainties have added up. Let's try some practice. 1.5 plus or minus 0.2 centimeters, seconds, plus 1.7 plus or minus 0.2 seconds. And that gives us 3.2 plus or minus 0.4 seconds. So again, we see that the uncertainties have added together. .5 plus or minus 0.5 millimeters minus 1.0 plus or minus 0.5 millimeters gives us 2.5 plus or minus 1.0 millimeters. You'll notice that even though we're subtracting the measured values, which are here, we're subtracting these values, we're still adding the uncertainties. So we still add the uncertainties even if we're subtracting the measured values. If we multiply measurements, then we add the relative uncertainties, and these are just uncertainties expressed as a percentage of the measurement that we make. So far we've been adding what we call absolute uncertainties, so it's pretty straightforward. We just add the uncertainties themselves, including the units. Relative uncertainties are a little bit different because really they're fractions, but we'll express them as decimal numbers. So here's an example: 5.0 plus or minus 0.5 meters divided by 2.0 plus or minus 0.2 seconds. So we can't add the absolute uncertainties because they have different units. It wouldn't make sense. So we convert them to relative uncertainties. So you can see that we have represented them as percentages of the measured value. So 0.5 meters is 10% of 5.0 meters, and 0.2 seconds is 10% of 2.0 seconds. So when we add, or rather divide those values, we get 2.5, but then we add the relative uncertainties. So we end up with a relative uncertainty of 20%, and our units will be meters per second. So we convert that from a percentage to a measurable value, so 2.5 plus or minus 0.5 meters per second. And we can see here that 20% of 2.5 is just 0.5. So we've converted it back to what we call an absolute uncertainty. So this is called an absolute uncertainty. Multiplying measurements works the same way. We just add the relative uncertainties. So let's try this one. So similarly, 0.5 newtons is 6.25% of 8.0 newtons, and 0.1 meters is 6.25% of 1.6 meters. 0.1 meters, rather. It's just coincidence that these values are both 6.25%. They could be very different percentages. When we add them together, we get 12.5%, and then we convert that back to our absolute uncertainty. So once again, here we're converting to an absolute uncertainty by multiplying to change from a percent back to the absolute. So 1.6 Newton meters is your absolute uncertainty in this case. Now you don't have to round your answer to significant digits if you are explicitly stating your uncertainty. So we only had 2 significant digits here. We can see here and here we have 2 significant digits. If we weren't using uncertainties, we would round this value. We would round this if we weren't using significant digits. But because we're using, or if we weren't using uncertainties rather, but because we're using uncertainties, we don't round the value that you see here. Often we'll use percent error to compare our experimental value to an accepted value. So to do that, we take what's called the absolute value of the accepted value, and we subtract the experimental value. So these symbols mean absolute value. Absolute value, which means we're only interested in the difference between them. We're not interested in whether or not the result in the numerator is positive or negative. So whatever we get in the numerator here, we just take it as a positive. And then we divide by the accepted value. And then we write that as a percent. So let's look at an example with percent error. Students measured the speed of sound in air to be 334 plus or minus 18 meters per second. The accepted value for the speed of sound at that temperature is 344 meters per second. What was their percent error? So the accepted value here is within the range of their possible values as indicated by the uncertainty. So they were not wrong. So we could say that within experimental error, the experimental value agrees with the predicted value or the accepted value. To calculate percent error, we'll just use our formula. So the absolute value of 344 meters per second minus 334 meters per second, and we get 3% when we work that out after dividing by 344 meters per second, the accepted value. All right, now you can get some practice with a lab activity.